onto the level 2 problems of the related rate word problems. Here we're going to do 3-word problems. That's all. And I want to try and just show you a few different things here. And the thing is, like, we got to take the words, translate them into mathematical symbols. Now I'm going to give you some detailed steps in the third video on the level 3 problems. And one of the things is like draw a picture and label things. If something's changing, we can put a variable in there. If it's not changing, we can use a number for it. And we're going to constantly translate the words into symbols. I remember when I first learned this stuff, once I started translating those words into symbols and writing down what I was given, like, hey, dy dt is equal to this, dv dt is equal to this, this is what I'm supposed to find, that just made things a lot easier for me. And then also that's always worth some good partial credit, you know, if we're good setting stuff up pretty good. And I'm just gonna stress like how to approach these problems the best that I possibly can, that we just need to practice and ask some questions here. Okay, so let's do first one. We're gonna drop a pebble in the water. You guys ever see that movie Pebble and the Penguin or something like that? I think like penguins, when they like another penguin, they give them like a pebble. So I think the next time I see a girl, like I'm just gonna like give her a pebble and then just see what her reaction is, man. Hopefully it'll be good, you know. And I don't know how that works exactly there, but that was a pretty good movie, man. Pebble and the Penguin or something like that. But anyways, we're gonna drop a pebble in the water, and you know what happens when you drop a rock in a rock? It makes that nice, beautiful ripple effect, right? Where these circles, these concentric circles, just radiate out and it makes a nice ripple effect right there. Now, what we're gonna do is like we're gonna have these problems change, and then we're gonna pause the problem. It's kind of like you're watching that ripple effect on TV, and you're gonna pause it at the instant one, you know, the circles are, you know, that big, all right? And then we're gonna analyze how fast things are changing, okay? And so let's say you got a stopwatch out and you just figured out that that radius was increasing at a rate of 5 centimeters per second. That's how fast those circles were radiating out from the center of that pebble where you dropped it. And then now if the circles are changing, the radius is increasing, right? The circles are getting bigger, the area of those circles are changing. So we're going to translate these words into symbols. When I say the radius is increasing at a rate of 5 centimeters per second, in symbols, what that means is the drdt. How fast the radius is changing is a drdt. That's 5 centimeters per second. When it tells me to find the rate of change of the area, they're asking how fast is the area changing. We want to find dA dt. When you typically have something like this, when that R is equal to 12. All right, so if we set that up, I think that's going to be a really like a springboard to help get some of these difficult problems corrected. You're going to try to turn this into a level 1 problem where you have everything that you need and then just go take a derivative and go to work on that, right? And then if you have stuff set up properly, I will try to get you some nice partial credit for that if we need to, all right? So anyways, you got to get your equation next, right? Now they're talking about circles, they're talking about area, so I'm going to start with the area formula for a circle. And then just in case you need those, on the last video, we had some basic geometry formulas right there, so you can pause and get those down again if you need to. Now, very important that you never use these numbers until after you take the derivative. So take the derivative first, everything with respect to time. So the derivative A with respect to time is going to be a dA dt. And here, this is like a number times x squared, a number times r squared. So you're going to multiply by the power, decrease that power by 1, but you just took the derivative of r's with respect to time, which means you simply got to tag on the dr dt. So there's your derivative. Now you plug in the numbers. You're supposed to find the dA dt. We were given that the radius was equal to 12. And then we are given that the dr dt was 5. So that's going to be 60 times 2. That's going to be 120 pi. And then we do need to get the correct units on this. On the AP test, they almost always ask for the correct units on a related rate word problem. And then so it's how fast the area is changing. That's how you know. If it's how fast the radius is changing, it's going to be single centimeters per second. How fast the area is changing, that's going to be square centimeters per second. And we're going to get exact answers on that. Let's do a ladder problem. These are really good problems there. You could do a few different scenarios with the ladder problem. I'm just going to do one of them with you here. But we got a 5-meter ladder leaning against the side of the house, and then something's going to happen, you know, like your dog's going to run there, bump the ladder, and then you're just going to start pulling away from the ladder, or your little younger sibling or something like that just messes with, starts pulling on the bottom of it. So if the bottom starts moving away, well, then that top is going to start sliding down the right. So here's my scenario. There's my house, and then here's the ladder leaning against the house. All right, so if this is the ladder, it tells us this is 5 meters. Now, when you're labeling your picture here, and I'll stress the steps, and I'll have them written out for us in the next video, but if it's not changed, that ladder is not changing. So you're just going to leave that as a 5. You can use a number for that. All right, but if it's changing, so what's happening here, the bottom of the ladder is being pulled away from the house. So this distance is going to be changing. You got to use a variable for that. You need a variable to represent that distance. And if that's changing, the top of the ladder is falling down the side of the house. So that's also changing. Now, typically, just my standard convention, if it's changing as horizontal, I like to use X's. If it's changing as vertical, I like to use Y's. If it's slanted, I like to use like a cursive S so I don't confuse that with a 5. But technically, you use whatever variable you want. But if you want to stay kind of consistent with me when I'm working out questions and whatnot, maybe just try to do that unless they tell you to use something else. Okay, so I got to translate these symbols here. I got to read the problem again. You can't just go straight to it. You're going to get yourself confused. You got to translate the words and the symbols. So it says the foot of the ladder. That means the bottom of the ladder is being pulled away from the house. So they're describing this at a rate of 0.4 meters per second. So they're telling you that's the X. That's how fast the X is being moved, okay? So I'm gonna write that down, that's my dx dt. And then you gotta think, is that distance getting bigger or is it getting smaller? If it's getting bigger, this is positive. If it's getting smaller, this would be negative, but that's gonna get bigger if the bottom starts sliding that way. So that's gonna be a positive 0.4 meters per second. And then it says determine how fast the top of the ladder is changing. So the top of the ladder, when you're pulling the ladder that way, the top of the ladder is going to be falling down the house. And so you got to figure out how fast that's changing. So we want to find dy dt. And then if I read the problem again, it says when the foot of the ladder is the bottom of the ladder is 3 meters from the house. So it's like you're just watching this problem on TV and you're just going to pause it at the instant that X, so when X is equal to 3. So you don't want to put the 3 right there because the X is not always 3. It starts off a little bit closer, and then you're going to pull it, and then eventually it's going to be 3. And we're going to pause it at that instant that X is equal to 3, and then we're going to analyze how fast things are changing right there. So it's important that whatever equation we use, don't use any of these numbers until after we take the derivative, okay? So get a picture. A lot of times that's helpful. Write down your givens. Write down what you're supposed to find. Write down what you're given, okay? So to always do that. I think that's going to springboard your brain to figuring out how to do these problems. And you're always constantly trying to turn it into a level 1 problem because there's less thinking involved right there. All your thinking should be done mainly at the beginning and in the middle of some of these problems here. Now, with the ladder problem, you got to come up with an equation on your own. So you're given info about X's and Y's. If I look up here, I think we could all look at that right triangle and say, hey, I need X's and Y's involved. Let's use the Pythagorean theorem. Let's go X squared plus Y squared equals 5 squared. You won't always use that, but a lot of times you'll use that, okay? If they start giving us like a theta or something like that, well, then that isn't going to help us at all. So there's our equation. And now I'm ready to just take the derivative and plug stuff in, everything with respect to time. So we're going to go 2x, tag on a dx dt, plus 2y, tag on a dy dt, and then the derivative of that is going to be 0. And then you're going to plug in as much as you possibly can. A lot of times you'll know everything. Sometimes you'll know everything but one thing, and then you got to figure out what that one thing is right there. And we got to do a little bit of extra work there. So we were given that x is equal to 3. We were given the dx dt is a positive 0.4. All right, I don't know what the y is. That's a problem. I'm going to have to come back to that. I also don't know what the dy dt is, but that's perfectly fine in my mind because that's what we're trying to ultimately figure out. So I understand that that has to be a variable right now, and I'm eventually going to solve for that variable. What's not okay that I don't know is this guy right here. I need that number in order to solve this equation here. So here's what you're going to do. You're pausing this problem at the instant that this x is equal to 3. So notice my original picture had a variable in it because it was changing, but at this instant, that's equal to 3. So usually when I'm working out the problem, I'll put like that in parentheses. I mean, at that time, that's going to be a 3 because you don't want to have the 3 in right there because you do the derivative of that, then you're going to have 0 and you won't have this whole chunk at all right there if you're not treating that like a variable right there. So if that's 3 at that instant, what I want to know at this instant, because I took the derivative, the problem is paused, I want to know what is the y at that instant. So now you can use your Pythagorean theorem, and that's going to end up being a 3, 4, 5 right triangle. So when the x is equal to 3, correspondingly, the y value is going to be equal to 4. And then you're going to solve this equation for the dy dt. So it's going to be 8 dy dt equals, you're going to get a number for this and subtract it over. That's going to be 2.4, I believe. And when you move that over, you're going to get a negative 2.4. So then your dy dt is going to be a negative 0.3. And then the units on that is going to be meters per second. It's how fast the ladder is falling down the side of the house. Notice what the negative gave us. We intuitively, we knew that ladder was falling down the house. And so we know that that answer is going to be negative. Sometimes we might forget a negative in our givens, and we might interpret our answer at the end, be like, all right, wait, I know that's getting smaller, so let me put that negative right there. Or if you want to go back and just look, maybe you missed up a negative here. Maybe this was supposed to be negative or something, and you just got to go back and kind of fix that. And then we're going to get exact answers for these. Remember our units always, and then we're good with that. Last problem. Look at that beautiful balloon I colored for y'all right there, man. Gonna get some trig involved onto this one, okay? So I wanted to make sure I squeeze in a trig problem because this is typically something that students have trouble with. So I'm hoping if I put some stuff like that in the notes, which I normally don't have time to do, hopefully that'll help us out. All right, so we got this balloon. All right, so you're walking around. I'm sure everyone had a balloon once upon a time in their life that maybe you let go and you're really, really sad as you watch that like just go up into the air and just go up to the heavens, right? So we got this balloon and we let it go accidentally or maybe on purpose, I don't know. And then, but what it gives us is we're timing this thing, the balloon rises at a rate of 8 feet per second from a point. And then we're gonna assume right now, because this is a multivariable calculus, we're gonna assume that it's not a windy day. So it's just gonna go like straight up for now, okay? And then once you get multivariable calculus, you could handle wind factors and stuff like that. But we're gonna find the rate of change of the angle of elevation when the balloon is 25 feet above the ground. Now, when you first read a related rate problem, most of the time, it doesn't quite make sense there. You read it too fast, you're not sure what's going on. You gotta slow it down for yourself. And I'm gonna get myself a picture here. So the balloon is going up. That's changing, so I gotta call that a variable. And then it tells us how, so I don't put the 8 right there. That's how fast that's changing, okay? That's gonna be a dy dt, but right now, so you're standing like over here, and then you're probably like crying a little bit. There's some tears just because you're sad because your balloon's getting away. But it tells us from a point on the ground, 60 feet from an observer, which means this distance is 60 feet. So you were upset, you just ran through a temper tantrum right there, 60 feet, and then you stopped and you looked up and then you started crying. So look, there's 60 feet. That's what we're locking in because we don't know multivariable calculus to account for the wind factor. Now, so once you get that that's 60, we can label that as a number because that's not changing, but the balloon is going up. So that distance is changing. We've got a variable right there. Now what I'm gonna do is just maybe just complete the triangle so we can have a triangle to work with. If you label this as an S, I mean, that's fine. I guess that's also changing, but you know, because that's gonna go up, but you don't really need anything with this. It doesn't give us anything about that. If I go y squared plus 60 squared equals s squared, that's not helping me because look at what it's asking us to do. It says find the rate of change of the angle of elevation. So the angle of elevation is that bottom angle. As you're looking up at the balloon, that's your angle of elevation. So let's translate these words into symbol. So that's changing, and then how fast it's changing. They're telling us how fast that y is changing is 8 feet per second. So what we are given is that the dy dt is 8 feet per second. And then it says find the rate of change of the angle of elevation, which means we need to find d theta dt, how fast that angle is changing. And then it gives us typically a when the balloon is 25 feet above the ground. So we're gonna pause it. So it's gonna go up so high. Once it gets to 25 feet above the ground, we're gonna pause it. So at that instant, the y is gonna be equal to 25 feet. So picture helps me. translating those words and symbols, reading that problem a few times and get all my symbols, got my givens down, got what I'm trying to figure out. And now I'm going to look at what equation I can use. A lot of times on the geometry problems, it's easy to know what equation because they're talking about the volume of this or the area of this, and you just go straight to that geometry formula. But right here, the Pythagorean theorem is going to help us. If you need to get a theta involved, you need to think SOHCAHTOA. That's what you need, all right? And if you did have an S right here, you're not going to use that. You always want to use the number involved because it's always easier to use a number instead of a variable. And then you got to use the other variable that you know information about. So you got to use the Y. You got to use the 60. So in relationship to that angle, that's the opposite side. That's the adjacent side. So we're going to go tangent of that angle equals opposite over adjacent. You want one variable on each side like that, if you can do that. And now we're going to take the derivative of everything with respect to time. So I know the derivative of tangent is going to be secant squared of that angle times by the derivative of the angle, which is just 1. I just did derivative of theta with respect to time. So we're going to tag on a d theta dt. This right here is the same thing as 1 over 60 times y. So the derivative of 5y is 5, the derivative of 4y is 4, the derivative of 1 over 60y is going to be 1 over 60. But you just did the derivative of y's with respect to time, so you got to tag on the dy dt. So let's plug in as much info as we have here. I got the 1 over 60. We are given that the dy dt, and I know that was positive because that distance was increasing. That we know that's going to be 8. The d theta dt, I don't know what that is, but that's all right because that's what we're trying to figure out. And here's the thing. On most of these problems, occasionally if I look at the problem and I see that's going to be a nice 30, 45, 60 degree angle, I'll use that. Most of the time it's not a nice angle, and most of the time I do not even calculate what the actual angle is and plug that in and do the secant. That's the power of the trig, okay? So let me share with you how to handle this. A very common problem that students do not like sometimes, but once you practice a couple of times, it's going to be the same thing every time you got the trig. Use SOHCAHTOA, and we're going to get the exact value for the secant of theta squared. So you know SOHCAHTOA, you know that cosine is adjacent over hypotenuse, which means secant is going to be hypotenuse over adjacent. So what I'm looking for right here, I'm going to do the hypotenuse over the adjacent side squared because it's secant squared. So I'm going to use my SOHCAHTOA, and we're pausing it at that instant that this y is equal to 25. And so now what you can do, that's 25, that's 60. Now at this instant, you can do your Pythagorean theorem. And then if you do that correctly, 25 squared plus 60 squared, you're going to calculate that hypotenuse is going to be 65. And so now you have the hypotenuse, which is 65. You have the adjacent side, which is 60. I'm going to actually just reduce that fraction before I square it. That's going to be 13 over 12. But see, now you're going to square that. And so you're going to insert that right here. So the secant is hypotenuse over adjacent, which is 13 over 12. And then you're going to square that, which is 169 over 144. The trig is completely gone. You don't have any more trig right there. That's the power of the trig and the SOHCAHTOA. That's why you did so much trig last year. So we could handle that. And know this is going to give us an exact value, not no estimated crap, not no estimating some angle that's not an exact answer right there. Now all you got to do is solve this for the d theta dt. So you got this 8 over 60. You can multiply by the reciprocal, the 144 over 169. You can use the calculator to help you out with that. And then when you simplify this, this is going to reduce to 96 over 845. Now here's the thing, anytime you do a d theta dt, the units are always, always, always radians per whatever your time measurement is. Our time here is seconds. This is going to be radians per second. So anytime you do a d theta dt, you're going to do radians per second on that. So hopefully those notes help. Now when you're doing the homework problems, these are going to help. You're still going to see some other scenarios there, but hopefully you can apply these to those other scenarios and do the best you can with that. And then we'll just go through practice problems and ask some questions and go from there. Thank you.